In previous few lectures, you have seen the important properties of Poisson bracket and also we have discussed the invariance of Poisson bracket in under the canonical transformation. Now today we will discuss a very important concept regarding this Poisson bracket. As you know, in classical mechanics, the equation of motion which describes a dynamical system are simply the Hamilton's canonical equation of motion. And we have studied these equations of motion in very detail in the previous lectures. Now, after getting the idea of Poisson bracket, we can see that the equation of motion of a dynamical system can be expressed in terms of Poisson bracket, and you will find its usefulness in the concept which will be discussed later on. In fact, in the equation of motion in terms of Poisson bracket is very convenient to remember, and its utility is also very large in discussing the dynamical problems. So let us see how we can express the canonical equation of motion or Hamilton's equation of motion for a dynamical system in terms of Poisson bracket. For this, let us start with the equation of motion or Hamilton's equation of motion of a dynamical system. As you know, these equations are given in like this: qk dot equal to del h by del pk. You know, here qk are actually the generalized coordinates, and qk dot represent the time derivative of this generalized coordinate qk. It means qk dot, as you know, this is in fact dqk by dt, and this is also known as generalized velocity. And the another equation of motion we write like this: pk dot equal to minus del h by del qk, minus del h by del qk. Here actually pk are the generalized momenta, and these are the canonical equations of motion of which you are familiar, and you have studied these equations of motion in very detail in the previous lectures. Simply we say that these are Hamilton's equation of motion. Now our aim is to express these equations of motion in terms of Poisson bracket. And for this purpose, let us consider a dynamical system, and we define a dynamical variable, let us say f. And this dynamical variable f of the system is actually a function of the canonical variables like qk, pk and t. Actually here this k runs from 1 to so on up to f, where f is actually the degree of freedom of the system. As you can see, the equation of motion is in terms of the time derivative of these canonical variables qk and pk. So if you want to know the equation of motion in terms of Poisson bracket, and as we have considered for this a dynamical variable describing the system denoted by the symbol f, which is actually function of the canonical variables qk, pk and t, then you must first of all find the total time derivative of this variable f. So let us find the total time derivative of this variable f. As you can see, since this variable f is a function of 2f plus 1 independent variables, you can see the values of qk will be equal to f. Similarly, pk has also f values and t has one value. So total number of independent variables is 2f plus 1. So definitely, if you want to find the total time derivative of this function f, you must follow the rule of partial differentiation. First of all, we will differentiate this f with respect to qk, keeping pk and t constant. After that, we will differentiate f with respect to pk, keeping qk and t constant. And finally, we will differentiate f with respect to t, keeping qk and pk constant. And so, in accordance with this rule, you can see that this df by dt will be equal to what? This will be summation over k del f by del qk dqk by dt plus summation over k del f by del pk dpk by dt and plus del f by del t dt by dt. Now as you can see, this dqk by dt, this will be simply equal to qk dot, and this dpk by dt, this is pk dot, and this dt dt is equal to 1, so the last term is simply del f by del t. Now you have seen the canonical equation of motion due to Hamilton, and these are qk dot equal to del h by del pk and pk dot equal to minus del h by del qk. So let us make the use of these equations here. In fact, instead of this qk dot, now we will write del h by del pk, as you can see here. And instead of this pk dot, we will write minus del h by del qk. So the RHS of this equation which you have obtained will now become like this. This is summation over k del f by del qk del h by del pk minus del f by del pk times del h by del qk. And I have taken this sign of summation before the bracket because in these two terms are in contain this sign of summation. Now see this first term in RHS of this equation. You have studied Poisson bracket, and from the idea of Poisson bracket or definition of Poisson bracket, you can easily say that this first term summation over k del f by del qk times del h by del pk minus del f by del pk times del h by del qk, this term is what? This is simply the Poisson bracket of variables f and h. See here. So the first term has been replaced by Poisson bracket of f and h with respect to a small q and a small p. But you can see I have not mentioned here as a subscript a small q and a small p, because you have learnt in the previous lecture when you have discussed the invariance of this Poisson bracket under canonical transformation that this specification of q and p is not needed, because when we will have the another basis capital Q and capital P, even then this Poisson bracket remains same. So there is no need to write here Q and P as a subscript. So I have not mentioned here Q and P. So in this way you can see finally we get that df by dt, which is equal to f dot, is equal to Poisson bracket of f and h plus del f by del t. Now as you can see that we have considered that this dynamical variable of the system f is a function of t2. But if you consider, sorry, there is some problem. see here. Sorry, there was some problem. Now the problem has been solved. So you can see, since here f is a function of t, so actually this term del f by del t appears here. But if you consider that sorry, we have to arrange the page. Yes, now it is okay. So if you consider that this f does not involve the variable t explicitly, in other words, you can say that if this variable f is not an explicit function of time, you know, in that condition, this del f by del t will be equal to 0. And if del f by del t is 0, you can say that in that condition, this f dot will be simply equal to Poisson bracket of f and h. Poisson bracket of f and h. I hope you have understand this these steps clearly. Now let us see. If you consider that this Poisson bracket of f and h vanishes, that is, it is equal to 0, then from this equation 2, you can see that this f dot will be equal to 0. So let us consider if the Poisson bracket of f and h is equal to 0. In fact, then you can see that f dot will be equal to 0. And if f dot is equal to 0, it means you can say that this dynamical variable f will be a constant of motion. So this result implies that the dynamical variable f will be a constant of motion. However, this requirement does not require that h should be a constant of motion. It means when f dot is 0, definitely you will say that f is a constant of motion. But when f is a constant of motion, it does not mean that h is also a constant of motion. H may or may not be a constant of motion. Even then, f will be a constant of motion if this Poisson bracket vanishes. So let us consider in this condition that this f is recognized as the generalized coordinate qk and the generalized momentum pk. Let us consider. So suppose such dynamical variables are qk and pk. Let us consider. In fact, we are now recognizing this dynamical variable f as qk and pk. So in this condition, from this equation 2, you can write, instead of F, we will now write QK and PK. So from equation 2, you can write QK dot, instead of F dot, now I am writing QK dot. And as it is equal to Poisson bracket of F and H, so instead of F we will write QK and H. And similarly, when you will write PK instead of F, then that equation will be PK dot equal to Poisson bracket of PK and H. PK and H. And let us say this is your equation 3. Now let us evaluate these Poisson brackets. What will be the value of this Poisson bracket? Now we should try to evaluate. So now Poisson bracket of QK and H. Apply the definition of Poisson bracket. You can see this will be summation over J del QK by del QJ times del H by del PJ and minus del QK by del PJ times del H by del QJ. This is just the definition of Poisson bracket. You can see. But see here, del QK by del QJ. Can you say what is this? In fact, del QK by del QJ. This is equal to delta Kj. And this will be equal to 0. Why? As K is not equal to J. And so this Kronecker delta is equal to 0. Sorry. And this will be equal to 1. Here don't write as. Not write as. And this is equal to 1 when K is equal to J. And at the same time you can see what will be this del QK by del PJ. Since Q and P are independent variables, so definitely the derivative of Q with respect to P will be 0. So del QK by del PJ, this is equal to 0. So in the above equation defining this Poisson bracket, the second term will vanish because del QK by del PJ, you can see this is equal to 0. So only the first term in RHS of this equation will remain non-zero here. And instead of this delta QK by this delta QK by delta QJ, we will now write delta Kj. So Poisson bracket of Qk and H will be what? You can see. Therefore, Poisson bracket of Qk and H. What will be this? You can see this is summation over J. See this equation. Del H by del Pj times delta Kj. So this will be del H by del Pj delta Kj. And as you know, you have seen also here that this delta Kj will be equal to 1 when K is equal to J. So taking K equal to J, you can see that this Kronecker delta will be now 1. And so after, since you put the value fixed to this index J, so now sign of summation will be removed, and this will be simply equal to del H by del Pk, because now I am putting here J equal to K. J equal to K. So here there will be del H by del Pk. So what we are getting here, this Poisson bracket of Qk with H is equal to del H by del Pk. But you can see this Poisson bracket Qk of H, Qk and H is equal to Qk dot. So you can see that Qk dot is equal to del H by del Pk. And what is this? You can see this is nothing, this is simply the Hamilton's equation of motion. This is Hamilton's equation of motion, one of the Hamilton's canonical equation. So in this way we can write the equation of motion in terms of Poisson bracket. Thus in terms of Poisson bracket, you can write Qk dot equal to del H by del Pk, and this is Poisson bracket of Qk and H. Qk and H. And actually this is one of the equation of Hamilton. Qk dot equal to del H by del Pk, and this is equal to Poisson bracket of Qk and H. Now we will evaluate the second Poisson bracket in equation 3, that is Poisson bracket of Pk and H. Pk and H. So again Poisson bracket of Pk and H. Let us evaluate it. From the definition of Poisson bracket, you may now write it summation over J del Pk by del Qj times del H by del pj and minus del pk by del pj times del h by del qj. This is just definition of Poisson bracket. Now you can see in this term this del pk by del qj. Since pk and qj are independent variables, so this will be 0. And del pk by del pj, this will be actually equal to Kronecker delta kj. Kronecker delta kj. So now the first term in RHS of this equation will vanish, and only the second term remains non-zero. So now you can write this Poisson bracket in this manner. Therefore, Poisson bracket of pk and h, this will be summation over j. See here, the first term becomes 0, and in second term there is minus sign, so write here minus sign, and the remaining terms are del h by del qj times delta kj. Del h by del qj delta kj. As you know, this will be equal to minus del h by del qk, because when k is equal to j, then this Kronecker delta will be equal to 1. And so what you get, since Poisson bracket of pk and h is equal to pk dot, you can see here. So you may now write this result in this way: pk dot is equal to minus del h by del qk. And as you know, this is nothing, this is the second equation of Hamilton. Second equation of Hamilton. And so this will be equal to pk h, Poisson bracket of pk and h. So in this way you can see we have obtained the equation of motion defined in this equation 5 and in this equation 6 in terms of Poisson bracket. So finally you can write here what are the equations of motion in terms of Poisson bracket. So finally equations of motion in terms of Poisson bracket. You may now write like this. You can write qk dot equal to Poisson bracket of qk and h, and pk dot equal to Poisson bracket of pk and h. pk and h. Actually, these are the equations of motion in terms of Poisson bracket. And you can see this form of equation of motion is more convenient than the equation of motion which we write in this differential form, because in the differential form you write the equation. When you write the equation of motion, then in this second equation there is a minus sign, But here symmetry is maintained. When you write qk dot, then that will be Poisson bracket of qk and h. And when you write pk dot, that is simply equal to Poisson bracket of pk and h. So there is no problem of minus sign here. So it is more convenient than the original form of equation of motion. Now from equation of this equation of motion in Poisson bracket form, if you consider that this Poisson bracket of pk and h is equal to 0, if we consider that, if you consider that Poisson bracket of pk and h is equal to 0. Taking this condition, we will find a very important result. So let us consider that Poisson bracket of pk and h is equal to 0. As you know that this Poisson bracket of pk and h is equal to pk dot, so if you consider that this bracket vanishes, then you can say that pk dot is equal to 0. Pk dot is equal to 0. And as you know, if pk dot is 0, what does it mean? It means pk is equal to constant. Because pk dot means what? Pk dot is simply dpk by dt, and if it is 0, then pk will be constant. That is, the linear momentum is conserved. And this conservation of linear momentum also implies that the corresponding coordinates are cyclic. You have, when you have studied the concept of cyclic coordinate, then you have seen if pk is equal to constant, which was denoted earlier by the symbol alpha, then the corresponding coordinates will be cyclic. Its conjugate coordinate will be cyclic. So this result implies that the corresponding coordinate qk is cyclic. Now we will see a very important fact here from this result. When you say that Poisson bracket of pk and h vanishes, it is 0, then you have seen that this pk is a constant, that is, it is a constant of motion, and its corresponding coordinate qk is cyclic. In fact, all functions whose Poisson bracket with Hamiltonian vanish, they are actually constant of motion. Or conversely, you can also say that Poisson brackets of all constants of motion with h must be equal to 0. So if you consider that if, let us consider any dynamical variable x. X is an arbitrary dynamical variable, and we consider that the Poisson bracket of this variable x with Hamiltonian is equal to 0. Then x will be a constant of motion. It means if the Poisson bracket of any function vanishes, Poisson bracket of any function and with Hamiltonian vanishes, then that function is a constant of motion. And its converse is also true. you can also say that if x is a constant of motion, then Poisson bracket of x and h will be equal to 0. So these two conditions may be combined in a single statement, that the necessary and sufficient condition for a function x to be a constant of motion is what? The condition is its Poisson bracket with Hamiltonian h must vanish. So you can write this condition in this way. Poisson bracket of x and h is equal to 0 if, this if means if and only if, that is necessary and sufficient condition, if x is a constant of motion. So this statement actually implies that if you consider that x is a constant of motion, then its Poisson bracket with Hamiltonian will vanish, and conversely you can say that if the Poisson bracket of x with h vanishes or it is equal to 0, then x is definitely a constant of motion. Actually, this fact is very important in constructing a constant of motion. So when we will see the numerical problems based on constant of motion, this idea will be utilized. So you can see what is the form of equation of motion in terms of Poisson bracket. So remember it, as I have mentioned in this equation A, that in terms of Poisson bracket you can write the equation of motion like this: qk dot equal to Poisson bracket of qk and h, and pk dot equal to Poisson bracket of pk and h. And actually these are nothing, these are simply the Hamilton's canonical equations of motion. And from this result you have seen that if we consider that x is a constant of motion, then definitely its Poisson bracket with Hamiltonian will vanish. And conversely, you can also say that if the Poisson bracket of any constant of motion with Hamiltonian is equal to 0, or in other words, if Poisson bracket of a function is 0 with Hamiltonian, then that function must be a constant of motion. So I hope you have understand the concept which we have discussed, and so in fact in the next lecture, using this idea of particularly constant of motion, we will see that how the Poisson bracket is used to find the constant of motion.